I wanted to start with these covers. 3 of them are covers of science fiction books, and 3 others are covers of science magazine, Nature and Science. So you can see that there is I don't know if there is a convergence in the methods of science fiction and science, but at least in the imagery, in the image, it's basically the same kind of thing. So, and I will come back to that because it's important, the way we represent our discoveries to the public. It's important to think about it, because if we say that we found an exoplanet that looks like that, while we just have a transit light curve, we may convey a wrong image about what we know about the planets, by trying to make something very realistic. So I will come back to that. So at least in terms of visual representation, we use sometimes the same tool, not in our research, but at least to communicate with the public. Here is a picture of where I work. It's in Bordeaux. So it's the tram stop, and behind the trees there is so here is the parking where we park the car, and our building is somewhere there. Why do I show that? It's because the stop is called François Bordes. François Bordes was a scientist, a specialist in prehistory, very important one, and he built the whole prehistoric research center at the University of Bordeaux. But he was also a science fiction writer. Under another name, because at the time it was not taken very seriously to write science fiction as a scientist, so he could have threatened his career. And Natasha is an expert on the story of François Bordes, so if you have questions about him, but I will show you some of the books he wrote under Francis Carsac. So this is one of the edition at the time. This is a translation in English, so there are not many French writers who are translated. There are some, so Francis Carsac was one of them. And this is a very recent re-edition of Francis Carsac. And at the time, so he would not say to his colleague that he was also writing science fiction. Now it's, I would say it's okay, and maybe there is a big difference between France and maybe English-speaking world. A famous example is Kip Thorne. Kip Thorne is a very, very famous scientist working on general relativity, black holes, for instance. And he was always fond of science fiction. He helped Carl Sagan to write Contact, because Carl Sagan needed a wormhole in his plot, and Kip Thorne theorized the concept of the wormhole. And in the years 2000, he wrote a script for the cinema called Interstellar. And first he approached Steven Spielberg at the time, and Steven Spielberg was okay to produce and direct the movie, and he was okay to accept the rule of the game imposed by Kip Thorne, which was nothing in the plot could violate the law of physics, and any speculations about physical laws that might still be imperfectly understood would nevertheless be grounded in principle that, well, at least serious physicists would discuss over a beer. That was his definition of the rule. Unfortunately, to me, because I really don't like the movie that the Nolan brothers made, but DreamWorks was sold, and Jonathan Nolan, the brother of Christopher Nolan, was hired to write the script, and the script completely forgot about this law. So there are many it's a very weird movie, because it was meant as a realistic movie, but there are completely basic stuff that are not respected. For instance, you take off from the Earth in a huge rocket, which is realistic, but then you take off from another planet, which is the same as the Earth, same gravity, with a kind of small, like the DeLorean in Back to the Future, while they say they're very realistic about a black hole. So they really forgot about that, and actually Kip Thorne became executive producer of the movie. He got the money from the producers to actually to fund this research, to make new models of black holes, and he got the Nobel Prize in Physics in 2016 for the discovery of the gravitational waves. So it means, what I wanted to say here is that you can write science fiction and still get a Nobel Prize after that. So it's not, we don't have the problem with Francis Carsac, etc. So that was kind of one of the most expected movie of all time. But it happened that it's the movie we dreamed of never existed. What basically Richard Feynman is explaining here is that, so it's a lecture, he's explaining that science is imagination. But imagination in a tight straitjacket. A straitjacket is, you know, this kind of jacket that restrains you to escape, a camisole in French. And this straitjacket are the known laws of physics. It means that in science, so basically, I try to illustrate this way. We have a core that we could call the consolidated science. It doesn't mean that it's a truth written in stone. It means that it has some power, for instance, predictive power. You can use this consolidated science, for instance, to build technology, to make prediction, very, very accurate prediction. So that's the kind of thing that's we base our research on. And the research, basically, it was what is between this consolidated science and the rest of the universe that is unknown, which is not understood in the same way, which is not modeled, which is not part of this of the things. And basically, so the game in research is that you can make hypotheses, you can invent things, just like a science fiction author would do, but you have to confront that to the real, basically you have to agree with the consolidated science, although you can, like Einstein, for instance, did not contradict fully the Newtonian gravity, but he made it more comprehensive. But you have to agree with all the observations and all the previous work that has been done. And what I think very interesting is that this research layer where we are here, and basically we are looking at the unknown, sitting on this on the shoulders of giants, as it was said before. It's something that is very unstable, that it's not consolidated by definition, the research. There are controversy, there are discussion, there are contradictions, and I don't know if Laurence will talk about this after, most of the science communication is done about the research. It's not done about the unknown, it's not done about the consolidated science, it's done about the latest paper that was published yesterday, which was not been incorporated in the consolidated science. It requires years to be confronted with observations, and all the public is want to know about the research. So it was really clear during the COVID pandemic that people were saying, oh, one day we are told this, one day we are told that, this contradict, or if you think about Mars, one day we've been told that there was water on Mars, the other day there was a contradictory information. Well, this is how research works. But maybe this is not what we should communicate in priority to the public. What we should communicate in priority to the public, it's the science that has reached a consensus. Or maybe to communicate about the unknown, because people need mystery in their life. And we have the chance, we are very lucky to be looking at something that somehow is supernatural, in the sense that it's not yet incorporated in our consolidated knowledge. And people want to know about that. And we don't speak enough, I think, about what we don't understand yet in science. And this extrapolation, we do it by expanding our knowledge, but the science fiction writer or author is looking at the unknown with its imagination, without the same straitjacket as the scientist. He could have this straitjacket if he wants to. We call this part of science fiction hard science, where you really, the author really wants to be exact relative to what we know. But you can also do Star Wars and don't care about the science. There are many ways in. But what I mean is that if we don't speak about what we don't understand yet, people who need mystery, everybody needs mystery, will go to take it somewhere else. So, for instance, I keep one example in astrophysics. We don't understand the rotation of galaxies. Galaxies rotate in a supernatural way. So we need to put some ingredient that we call dark matter to get what is observed compared to what we should have based on the current theories. So we need this other ingredients that is dark matter. There is the same for the expansion of the universe, which is accelerating. It doesn't work with the standard model, so we need to inject something that we call dark energy. Everything that we don't understand is dark. And it's a very important field of research because we think that here there is a breakthrough into a novel physics. The physics of super high energy, where the consolidated part of science is not doing a proper work at the moment. And it's very important to say that there is supernatural things in the world. It's just not on our doorsteps. It's not ghosts, it's not aliens coming in our garden, but there are some very fundamental stuff we don't understand. And if we don't explain that to people, and if we don't share this sense of wonder that we have in science, they will go to other kind of cheap mysteries, like the pyramids were made by aliens a few thousand years ago, like people like Avi Loeb will try to convince you that there is a dogma in science that prevents us to work on things like UFO, or who say that the first time an object is crossing the solar system coming from another one, Oumuamua, this asteroid or comet, or it could be an alien spaceship crossing. And these guys, they have a lot of attention, they have a lot of views on media, and we have to compete with that. So I think we have to sell a bit of mystery, and maybe science fiction is an ally when doing that. I have two very important examples for me when I communicate to the public using science fiction. One is Les Entretiens sur la pluralité des mondes, de Fontenelle, so Conversations on the Plurality of World, which is old. It's from the end of the 17th century, and I love this book, and I advise you to read it. It's short, and it's really fantastic. So the idea of this book is to look at the planets in the solar system, the known planets at the time, and the known moons, and to wonder what could be the life there, and especially the life of a society, not really just animals, or what could be societies on the Moon, on Mars, on Mercury, on Jupiter, on the moons of Jupiter, considering the astronomical properties of these bodies. So for instance, if there are people on the Moon, what do they see when they look at the Earth? They don't see human beings, they don't see life, so for him. So maybe there is life on the Moon, just we cannot see it. And what is very important in this book is that he makes a very clear distinction between what's the fact and what's the speculation. So he's not trying to explain that there must be life on other worlds. He's not trying to explain that every star in the sky is another sun with a planet. Actually, there is an incredible passage in the book where he says, I don't know, maybe this star has no planet, maybe this star has 2-3 planets, maybe this star has a very close by planet, maybe he's already thinking of the possible diversity that the planetary system could take, and he say, I don't know, I'm just inventing, I'm just doing poetry. But I'm using what I know from science to, for instance, he will say Mars is not very interesting, it's basically the Earth. It's a little bit smaller, it's a little bit farther away than the Sun, but it has a similar obliquity, donc seasons. The duration of the length of the day is about the same. I have nothing interesting to say about Mars because I don't see what could be different. Maybe it's a little bit colder because it's farther away from the Sun. He doesn't know about gravity at the time. Newton was working at the same time on gravity, so he doesn't know about it. And at the opposite of that, there is an author, a scientist and author who is very famous in France. It's called Camille Flammarion. And he worked about the plurality of inhabited world. And he's using science to impose the idea that there must be, science tells you that there is life on Mars. And there is life that is, because of low gravity, there is life in the skies of Mars, much more than in the sky of the Earth. There is this kind of life on Venus, there is this kind of life on Mars, and is really having this authority argument to impose that. And it makes a kind of very blurry distinction. There is no distinction basically between speculation and science in Flammarion. So it was very popular because he delivered the mystery and the interest, but he was not as rigorous as Fontenelle, and I think we pay today what Flammarion did, at least in France, in terms of making people believe that scientists were convinced that there was life on Mars, etc. Because of this kind of way of basically projecting what we have on Earth on other planets, it's interesting that basically, if you look at the history of the observation of Mars, and you see how it's described in the literature, not in science fiction, but also in science fiction, it was like we were the witness of the end of a world, of a living world. Basically, at the end of the 19th century, there was a lot of life on Mars. There was agriculture, there was channels, and as our observing power increased, we saw that vegetation disappeared, and basically now life is in some niche under the soil and in the form of very simple molecules. So it was not seen as just the fact that the progress of observation was revealing us the true nature of Mars, but like we was witnessing the end of a world that in just 1 century was dying. And it's really described even in scientific book as a dying world where there are only a bit of vegetation remaining. So I don't want this to occur when we observe exoplanets with a growing observability power. But to show you how important it was, in the French Academy of Science in the year 1900, there was this prize, this award called the Guzman Award. It was a large amount of money for the time, and it was meant to be given to anyone who would send a message to another object in the sky, a planet, a star, and receive an answer, at the exception of Mars. So basically, if you send a message to Mars and you receive an answer, you don't deserve the prize. Everybody knows that there is a civilization on Mars. We don't care. If you send a message to Venus and you receive an answer, you get 100,000 francs. So to give you an idea, this was sponsored by the French Academy of Science, to give you an idea of what was our representation, a perception of Mars. I'm jumping to something completely different. I don't know if you know Sean Raymond. He was there yesterday, but to record not to give a lecture, I think. But he has a website called Planet. So you search Sean Raymond Planet. And he uses, he does kind of mind experiments, science fiction mind experiments, to teach you about some important concepts in astrophysics. Have a look. It's a great way to learn about, for instance, planet formation. And he has, for instance, he tries to build the ultimate solar system. So he tries to put as many habitable planets in one single system as possible, and he does it step by step, and after some time he finds a new idea. So I think at some point he managed to put 1 million habitable planets around the star using black holes and a lot of funny stuff, using retrograde orbits, and so have a look, it's really great. Another way that science fiction has been used by European Space Agency as a survey to look for concepts or technology, innovations that could be useful for space exploration and space application. So basically, they had this cell of people reading science fiction to see if there are ideas that could actually be useful for, I don't know, the International Space Station, etc. So they discuss, for instance, I just took an example, they discuss propulsion using antimatter. How is it described in science fiction, and what could be possible applications of that? Another thing that is not often discussed is the fact that actually this straitjacket that Feynman is talking about, as a scientist we don't have a choice to wear it, we have to wear it. But why a writer would want to wear a straitjacket like that? And it's because constraints produce creativity sometimes. When you don't have the means, you don't have as many, for instance, if you're making a movie, if you have too much movies, sometimes it's a crappy movie because you don't have to use your imagination to try to find a solution. A great example in cinema is the movie Jaws by Steven Spielberg, again, is that the movie was meant to be based on a giant shark, mechanical shark that never worked. So the director needed to find a way to convey the idea that there is a giant shark without showing it, and actually it's a movie that is taught in cinema schools today because of that. So for a scientific, for a science fiction writer, this constraint of law of physics can be a way to create, to force the imagination to go where you would not go by yourself. And an example of that is a very famous science fiction book called Mission of Gravity. He had two different titles in French. And so the author, Hal Clement, described in an essay exactly why he did that. So the idea of this book is that it's a planet with a very high gravity, very, very high gravity, that's rotating super fast. So it's a flattened planet like that. And the idea is that there are some human explorers who need to go on this planet to recover a probe that crashed on this planet. And the probe crashed on the pole of the planet, and because the planet is rotating super fast, the gravity that you feel is much lower at the equator than at the pole because of the centrifugal acceleration. So they can survive at the equator, but they cannot survive at the pole. So basically the idea of and when he started to write the novel, he said, I don't know how they're going to do. I'm curious about how they're going to make it. I need to find a solution. So he wrote a book trying to find a solution, and in the book there are living species on the planet, and he will use them to basically to make an expedition with them to go on the pole and recover the probe. And he was really using this straitjacket of the law of science to find a new storylines, if you want, in this story. And that's something that we should discuss with science fiction writers. Those who really want to be constrained by the science are looking for that. They don't know the answer when they start to think about the book, and they will have to find a solution. So they are the first readers of their story. They are the first to discover what's going to happen. Some funny well, I think entertaining stuff. So this is a stellar system very nearby called the 40 Eridani. So it's a triple system. This is 40 Eridani A. It's a sun-like star. And it's orbiting with a pair of two dwarfs. It's a red dwarf and a white dwarf. So this is a star that exploded and that became a white dwarf. And this is a red dwarf. And it also has another property. This planet is the home planet of the Vulcans. It's a home planet of Spock. If you in the Star Trek episodes and movies, they say that Spock is coming from a planet around 40 Eridani A. And it's interesting because in 2018, a planet was found around 40 Eridani A. And so the fans of Star Trek are really aware of this kind of stuff, and they knew about that, and they made a lot of pressure on the International Astronomical Union. So we called this planet Vulcan. So at the time I heard about that, and I said, but it's stupid, because if you call this planet Vulcan, and then in 2 years we find another planet in this system that is more like the one of Spock, then how are you going to call it? You will have Vulcan, and then another planet that, no, that's the real Vulcan, and then another planet that, no, this is really the new Vulcan. So at the time I discussed with some of the fans, I say, maybe wait a little bit, it's too early, this is a giant planet, it's not really interesting. And recently there was this paper, like 2 weeks ago, where actually they find that, so it was a radial velocity signature. So there was a variation in the velocity of the star that was interpreted in 18 as a signature of the planet, and they found a correlation, a very strong correlation with the magnetic activity of the star, which means that the exact orbital period of what was thought to be a planet is actually the rotation of the star, and that's bad. When we find a radial velocity period that is exactly the period of the rotation of the star, it's bad. It means that what we are, the change in the apparent velocity of the star is just due to some intrinsic motions on the star. So this planet disappeared a couple weeks ago, so it was a good thing not to call it Vulcan. There might be some planets around this system. So, but there are super interesting things I discussed at the time with the fan of Star Trek, and say, imagine here there is a white dwarf. So it means that there was a supernova in this system. So what about the planet here? What happens to the ancestor of Spock when there was? I say, oh, that's super interesting. We need to write about that. So there are things to. So it's interesting because we also had the planet in the solar system that was called Vulcan and that disappeared. Did you know about that? So I don't know if you know about the discovery of Neptune. Neptune was discovered by there's a, depending on where, if you read that historical book in English or in French, but at least there was this French astronomer called Urbain Le Verrier, who actually he was looking at the orbit of Uranus, and he was saying it's not a Keplerian orbit. I can see perturbations from Jupiter, Saturn, but I see another perturbation. There must be another planet, and he was able to infer the existence, the orbit, and the position of Neptune, saying, observe here. They took a telescope, they observed, and there was here was Neptune. So it was a really exceptional achievement. But then he also saw another unexplained perturbation on the orbit of Mercury. And the only, in the Newtonian view of gravitation, the only way to explain that was to have a planet between the Sun and Mercury. And he called this planet Vulcan. And he tried to spend all of his life trying to locate this planet or these planets because there was no very satisfying solution to that. And the reason is that this perturbation compared to the Keplerian orbit in the orbit of Mercury was due to general relativity. It's called the advance in the perihelion of Mercury, and it was explained by Einstein in 1915. And so the poor Le Verrier, with his tool, a Newtonian tool, he needed a planet between the Sun and Mercury, and it was very difficult to look at it because it's really towards the Sun, so it's not very easy to confirm or not. And he chased a non-existing planet called Vulcan, and so at some point with Einstein, Vulcan disappeared. So there is a kind of tendency in Vulcan planet to disappear at some point. This is a personal anecdote. So this is a plot that I made in 2007. Because there was this, for the first time, we discovered a system where there was a planet in the habitable zone of a star and a planet that was not a giant. It had a minimum mass of about 8 Earth masses, which could put it in the telluric or in the terrestrial range of planets. This star was Gliese 581, and this was planet D. So with Jim Casting and other authors, we wrote a paper about the potential habitability of this planet. We made some climate simulation and stuff like that. And it's actually probably my paper that's the most cited. And this planet does not exist. Just like Vulcan, its period is totally correlated with the rotation of the star and the activity of the star. So it doesn't exist. So I've done science fiction. I have written about the climate, the properties of a planet that does not exist. So I am a science fiction writer, and I'm allowed to give you this talk about science fiction. Fortunately, I heard about that not in a, not just one day it existed, and the other day it was a long process, and it was a long time ago. If it would have been found out 1 year after that it doesn't exist, I would have been really depressed. But now I can joke about it. So Alpha Centauri is the closest stellar system from the Sun. It's made of 3 stars. There is a pair, A and B, a pair of Sun-like stars. Not very close, but the 2 stars are separated by about 20 times the Earth-Sun distance. So about the distance between Uranus and the Sun. So there are 2 stars. And there is another one. Star C, which is like 15,000 Earth-Sun distance away from this pair. We call it Proxima because at the moment it's closer from the Sun than this pair. It's Alpha Centauri C or Proxima. So this is not part of this system. So it's a very important system because it's very nearby, it's very bright. At least because we don't even see this red dwarf here in this visible picture. So so here is a picture of in X-ray of the pair here. And it's always been very important, of course, theme in science fiction. There is a famous short story by Van Vogt called Far Centuries. It's a very interesting concept. He developed that, and the idea is that at some points in human history, there is a spaceship that goes to Alpha Centauri because they know that there is a planet that you can colonize. So they sent a spaceship. I don't remember in the story if it's one of the 3 stars. I don't know, but it's a travel that takes I don't know, centuries. So they are hibernating, they are sleeping. It takes centuries, and when they arrive to the planet, it's already colonized. It's centuries in the future, and when they arrive, there are cities that have been built with their names because they're like heroes. Because meanwhile they were traveling, the progress made the travel between Earth and Alpha Centauri very easy, and like people go on weekend and stuff like that. So for some reason in the story they were never able to intercept the spaceship, but they were waiting for. What is interesting is that was an actual problem in solar system exploration, and in particular to send a mission to Pluto. So Pluto was very early, a very key target in solar system exploration. People wanted to see, to learn about Pluto. But the first concept would take like 30 years to reach Pluto. And some scientists were saying, okay, if we send a probe that will take 30 years to send a few kilograms to Pluto, and maybe in 10 years we will send a probe that takes 10 years to go with more utility charge payload there, and it will arrive 10 years before the one that we sent. So it was actually an actual problem, and at some points when they reach a travel time of 10 years, they decided that it was okay, there would be no prospects of propulsion that could beat that, and they sent New Horizons probe. So there was an idea that's actually a real concern when you want to send something very far away. There is probably some of you have read the three-body problem and the sequels. It's very important because it was a big success in science fiction books, and it's a Chinese author, so and it's really good to read. And the idea is that basically there is an invasion from Alpha Centauri, which is not actually Alpha Centauri in the book. It's called Trisolar. It's exactly at the same distance as Alpha Centauri, but it doesn't have the property of Alpha Centauri, and that's a bit of a problem for us because actually this book doesn't take place exactly in our universe. It's a kind of parallel universe where the physics is different, the properties of the stars around us are different, but it's never said, and it's only the physicist or the astrophysicist that is clearly that understands that we're reading. So I have a lot of questions about Alpha Centauri based on what is described in the three-body problem. But the idea in the book is great, is that there is we understand that there is a fleet of spacecrafts coming to Earth, probably with bad intention, and we know it will take 400 years, and so we have 400 years to prepare. And it's the story of these 400 years. How do we prepare to this fleet, this threatening fleet of spaceships? That's it's a great idea, and you see the evolution of society during this period, and from a Chinese point of view. Okay, so just to say that it's an important, of course, it's also the theater of the most successful movie in history. Okay, Avatar. So in Avatar, Alpha Centauri A has a giant planet, and this giant planet has a moon called Pandora, which is habitable and inhabited, and where humans go because they are interested in the resources of this planet. So you know about that. With Sean Raymond, we worked a little bit about that, and we wonder, is it possible for Alpha Centauri A to have a giant planet first? Because it's a very nearby system, and we know how to detect giant planets. It's becoming quite easy. So for such a bright system, we should have very strong constraints about the planets on Alpha Centauri. So there is still room for little planets, but not for a big one like Polyphemus in the movie. So we look at the constraints from radial velocity, and we say, okay, there is no place for a giant planet except. So this is how actually the system is looking when you look from the Earth, except if the Polyphemus orbit is on the plane of the sky, because in this case there is no radial velocity signature, because there is no radial motion in our direction. So if the planet is in this orbit, we would not see it. But because of the geometry of the system, this orbit is not stable. It will come back to the plane of the two stars. So we show that actually this planet cannot exist, and we say, okay, it was a joke for us. But Sean was called by the production of the movies and by the James Cameron team to be consulting on the next movies. So we were very happy, but actually the idea was just for us to sign a non-disclosure agreement. So, but I speak about it anyway. So we were saying, oh, we are going to participate to the Avatar sequel, but we never had a phone call, nothing, not a letter. We were very sad. About representation of exoplanets, so if you look about Proxima B, the Proxima B exoplanet, if you Google it, you will find a really nice view of this planet. So comparison between the Earth of Proxima B, views from the planet looking at the star. And actually the only thing that we know about this planet is that it's a variation in the velocity of the star, which has a period of 11 days. Now we have seen new periods from another planet, maybe another one. So we don't even know the actual mass of the planet. So even less its radius. So there is an issue here, because some people they Google and they think we know much more about this planet than we actually do. So we have to think about, we have to get interested in science fiction and the speculation about what it is, because if we don't, we do it anyway, but without control. So we need to keep in mind that we are using imagination and speculation as a way to convey our scientific work. So we have to be conscious of that, otherwise we will do it anyway without having being aware of that. So the only thing that we know is that there is a planet with an 11-day period. We know that with the properties it's set in the habitable zone of the star. I had here a scene from this movie, Battleship, where the habitable zone is defined, but I don't have the sound. But I will try to. I don't know if I remember, but basically it says if your planet is too far away, it will be frozen. If it's too close, it will be burnt. And if it's at the right distance, it will be perfect for life. And the guy is okay. The scientist, okay. So I think it's a very short version of the lecture you had by Martin. You should use it next time and then go walk in the park. So another thing that's interesting about Proxima Centauri, and I am sure that Martin, you talk about that, is that because of tidal effect, this planet must be in synchronous rotation by showing always the same hemisphere to the star, like the moon to the Earth. We always see the same face of the moon. It's the same if this planet exists. I'm always careful about that. We think there is a planet. If it exists, we are very confident, because we're using this consolidated part of science to say it, that tides should lock it. And so Martin, for instance, is one of the experts of studying the climate of this planet that have a synchronous rotation and which have a very peculiar climate. And actually he was the first to work on Proxima B during his PhD and to make the first climate model of this planet. This was described in a science fiction book by Brian Aldiss. What was it, the 60s or the 50s? I don't know.
1962.
Okay, so the early 60s. So it has two different titles. It's either Heat House or The Long Afternoon of Earth. So the idea is that it's in the distant future of the Earth. And in the view of Aldis and his knowledge of tides, the tidal interaction between the Earth and the Moon and between the Earth and the Sun has synchronized the whole system. So basically, the period of rotation of the Earth is 365 days. So it's synchronous with its orbit. And the Moon is also in orbit of 365 days around the Earth and around the Sun. So it's in the Lagrangian point of the system. And so it makes a fixed triangle. And in the book, because everything is kind of in a rigid motion, there are spider webs between the Earth and the Moon that you can travel with the spiders from one to the other. But at least so he believed that this was the fate of the Earth, while actually we know that when the Sun will become a red giant, basically the evolution of the rotation of the Earth and of the Earth-Moon system will be very little compared to what we have today. It will not be a very big evolution like that. But it's interesting that, so here are some climates. So this is done by Jérémy Lecomte, but Martin has also some modeling. So in 2017, we announced the discovery of a very important system called TRAPPIST-1. Very important because it offers us observational possibilities that are completely unique. So there are at the moment more than 200 hours of observation with James Webb trying to characterize these planets. We were able to determine their mass with a few percent precision. We are trying to detect, to know if there is an atmosphere on this planet. So when it was published in Nature, we were aware of this problem of representation. So we imposed actually to Nature to have a presentation where it was obvious that it was some model or some. So we wanted to have it like put on a table, and so it's not a photography. So it probably conveys some ideas, like there are some rendering of the planet, but at least we know that this is not an image of a planetary system. And what we did is that, so there was this science fiction writer called Laurence Suner. She lives in Switzerland, and so part of the team we discovered the system. There were people working in Geneva who knew, we were friends with Laurence, and Laurence was aware of the discovery of the system very early, and she wrote 2 short stories about stories occurring in the TRAPPIST-1 planet with human settlers in the distant future. And we had this short story translated, and it was published in Nature with the discovery of the planet. So here is the science fiction story. So we had to read it carefully to make it very compatible with what we knew. And actually, while working with Laurence, we found about stuff that we would not have thought about without. For instance, what the appearance of the planets from one planet to the other. It's a very compact system, and actually, tonight, if the sky is okay, you can see Mars and Jupiter, and these are just spots that are a bit brighter than most of the stars, but that's it. In the TRAPPIST-1 system, if you are on this planet and you're looking at this one at the conjunction, it's like the full moon. So it's interesting to think about that, and so so in the second short story, I was reading it, and Laurence at some point mentioned a geostationary satellite in the system, and I thought about it, and I said, I don't think it's possible. The system is too compact, and because the planets are synchronous, you need, so for the Earth, the rotation is 24 hours, so you need a satellite with 24 hours orbit, which is 36,000 kilometers away. It's not that far, but here the rotation period is the orbital period, like on Proxima b. So the geostationary satellite must be at the Lagrangian point, like in the Brian Aldiss book. And I told I don't think this is stable. So I discussed this with Sean Raymond, and Sean Raymond, oh, that's a cool question. I will make some simulation. So he put a lot of stuff in the Lagrangian points of the system, and he made plenty of simulations. He said, no, it's not stable. It goes away very quickly. Okay. So I told Laurence, no, you have to remove that. It's not compatible. And years after, I discussed with Sean, and I say, you remember when we did that? You said it was unstable. So how quick was this instability? I said, oh, 10,000 years. 10,000 years after that, it's gone. So for us, astronomers, it's unstable. We are not hoping to find an object there. But for settlers on a planet, who cares about if your satellite is away in 1,000 or even a century? I think the longest geostationary satellite we have lasted like something like 20 years. So I called Laurence and I said, I'm very sorry you could have let your geostationary satellite. We are really bad at this work, sorry. So sometimes you have to think about... Of course, there is a famous example. I told about Alpha Centauri, which is a multiple stellar system. We are now finding circumbinary planets, so planets orbiting around binaries, like this one. And basically, so Star Wars is not a story based on science, but actually this vision, this concept, is actually fairly simple, and it works, and there are planets like that out there, and it turns out that we scientists, we call this planet Tatooines. It's like the word we use even in the title of the paper. So in this paper they really put it far, because they say on the fate of unstable circumdary planets, Tatooines close encounters with the Death Star. So they put two references to 1977 movies, Close Encounters of the Third Kind by Steven Spielberg and Star Wars by George Lucas. So so there are also systems where you have two stars, and each one of them can have its own stellar system. We also find that there are plenty of them, because many of the star systems are widely separated. So there is a lot of room in the system, and this was explored by, again, Brian Aldiss in a series of books called Heliconia, where actually, because of the stellar orbits, one of the stars is a giant star, and when the star with the inhabited planet comes nearby, it makes a kind of season that lasts for a brief period of time, and then there is a long winter. So it's interesting, and recently I was contacted by a science fiction writer who wanted to have a system with both stars having their own planetary system and with inhabited planet on both in both systems, and he wanted to have some kind of climate change due to the orbit of the star. So I told him, well, it's complicated, because if you have like in Alpha Centauri, if you have planets, you can have the star that come very close, otherwise it would destabilize the system. So, and I did I did two things. I gave him a Python code to build this planetary system, so he can really add planets and see what happens, and see the change in insolation. There is no climate work in that. It's quite simple. But when I did that, I played with it. I saw that there was always the same eccentricity value, like something like 0.4, to maximize the climate change in the systems. And so I really wrote the equations, and I found that actually I can find a maximum in eccentricity. And so I will find time and write a scientific paper about that, and I will include the writer in the authors of the story. We'll end with with something that I did for a science fiction novel that it was a lot of work, and I want to reassure if there are science fiction writers in the room, you don't have to do that to write a science fiction book. But so I was working on the effect of obliquity on a planet. So this is the Earth, which has quite a low obliquity. So we have polar caps, and basically the coldest part of the Earth is the pole, and the hotter part is the equator. But if we would have an obliquity higher than 50 degrees, this would be the opposite. In average, during the year, the coldest part would be the equator, and the hottest part would be the poles. This happens sometimes on Mars because of this chaotic change in obliquity. And we see the traces of ice on the slope, for instance, of the big volcanoes that are at low latitude. So we know it happened. So this is this shape. So this is the latitude, and this is the mean insolation as a function of latitude over a year. So we are here, and we can see that the insolation is maximum at the equator and minimum at the poles. Okay, but above about 50 degrees, so above curves like that, we have this shape where the coldest part is the equator and the hottest part is the pole. So basically, there are different climate solutions. You can have, depending on the obliquity, so if you play with an aquaplanet, a planet covered with water, everything that's red and yellow is liquid water, and everything that's blue, it's ice. So you can have an icy planet, you can have a purely liquid surface. So we have permanent polar caps, you can have seasonal polar caps, and you can have this kind of icy belt on the planet, or the contrary. So I was interested in that, and I say, oh, if I would be a science fiction writer, I would be interested in a planet like that, where there is this impossible barrier, very cold. And what about life that's here and life that's here? They could have evolved completely in different ways, and maybe there is a civilization emerging here and wondering what's in the other side, and maybe there would be some interesting stuff to write. So I'm not a writer, so I contacted a science fiction writer and say, is this story interesting for you? He said yes, and he wrote a novel about it. And actually I did, with the help of Martin, I did some simulation of the climate of this planet. So, and on this planet you have seasonal oceans at the pole that open and disappears with time. So I can give him the length of the day, the insolation, the sea ice. So here you see an ocean, and it will close at some point. And here you will see the opening of the southern ocean. We have the temperature, clouds, rain, snow. And so he did, you know, when you read a fantasy or science fiction book, sometimes there is this map, very important map that you never go back to it because it's boring to read the map. But it was interesting for us, so he designed the map with altitude levels, and Martin had a code to translate that into the topography of the GCM. So I really used the real topography to do the simulation. And so there is a continent called, by the settlers, called Australia in the novel, and I could provide the weather. For instance, these are 3 days at the spring equinox, so it could show him what was the speed of the winds and stuff like that on the thing. And I can stop here on this crazy work that maybe you will find completely useless, or I can keep going for a bit, but if you have questions I can stop here. Just tell me. Okay. So maybe just one concluding remark. So with Natasha, we have founded a science fiction festival. So she is the president of it. She's the mastermind behind it. And last year, the topic was hopeful futures, utopia. Basically, the idea was governments and politicians are not able to provide us a vision of a future that we want to go there. They are stuck with the way the world, the society works now, and they are not able to imagine the future world that we need. Actually, we need something to project. So the idea was that maybe we can discuss with science fiction authors and writers about what could be a future that is not a dystopia or the end of the world, The Last of Us or Walking Dead. So it is something more. And there is a how do you say a science fiction genre that is emerging, that is sometimes called hop punk or solar punk, that is about that is about a different future. So that was the topic last year, and we will. So it's in French, but we will soon release the video because everything was recorded. And the next topic will be monsters, which is also cool. Sorry, that will be in September near Bordeaux. So that was to end and to say that we can do science. So the idea is to have scientists meeting and speaking with writers.